Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a pretty hot topic, learning adaptive parallel reasoning with language models. It's a mouthful, but it boils down to how we're trying to get AI to not just process language, but actually reason and do it in a way that's adaptable and, importantly, that in parallel, much like our brains do.
Yeah, I saw that paper floating around. It feels like we're edging closer to AGI with every new iteration of these language models. The scale of these things is just mind-boggling. I mean, we're talking about models trained on massive data sets, processing information in ways we couldn't have even conceived of a decade ago.
I'm a little more skeptical, I think. While the progress is undeniable, I'm not convinced that just throwing more data and bigger models at the problem is actually getting us closer to true reasoning. Are they really understanding, or just mimicking patterns in the data?
I'm with Sarah to a degree. It feels like brute force. We're throwing computational power at the problem without truly understanding how intelligence works. I think a key element is missing, something to do with how the brain represents space and time and translates between different coordinate systems. Current systems are so data hungry and inflexible.
That's a great point, Donald. It's like they're really good at recognizing patterns, but not so much at understanding the underlying relationships or applying that understanding to new situations, which, in my opinion, is where that adaptive part of adaptive parallel reasoning falls short in current language models. They can adapt to some degree, but their reasoning is often brittle and lacks true flexibility.
But look at the progress. Think about how GPT-3 can generate code, translate languages, even write poetry. It's not perfect, sure, but the potential is undeniable. And with each new iteration, the algorithms are getting smarter, more efficient. Isn't that by definition getting closer to AGI?
It looks like reasoning auto, but is it really? I mean, if you ask it a question that requires a bit of common sense or real-world knowledge that wasn't explicitly in its training data, it often falls flat. It can generate grammatically correct and even stylistically impressive text, but the underlying understanding just isn't there. It's like a really sophisticated parrot.
Exactly. And that's because it lacks that fundamental understanding of space and time. If you asked it to, say, plan a route to a restaurant, it might be able to generate a plausible set of instructions, but it wouldn't actually understand the spatial relationships between the different locations, or how those relationships change over time as you move through the environment. It's just stringing together patterns it's learned from maps and directions.
And that's where I think we need to look more closely at the brain. One study showed surprising similarities in brain activity patterns during complex problem solving, suggesting biological inspiration for AI reasoning architectures. We need to move beyond brute force and start incorporating more biologically inspired mechanisms. Think about how the brain handles parallel processing. Different areas work together, sharing information and adapting to changing conditions. We need to figure out how to replicate that in AI.
Okay, but how? I mean, we have a pretty good understanding of the macro level of brain function, but the micro level, the actual algorithms being implemented by individual neurons, that's still largely a black box, right? How can we translate that into something we can actually implement in silicon?
That's where neuro-symbolic AI comes in. It's about combining the strengths of neural networks, their ability to learn from data, with the strengths of symbolic reasoning, the ability to represent knowledge in a structured, explicit way. So instead of just throwing raw data at a neural network, you would feed it structured knowledge represented in a symbolic language, and then use the neural network to learn how to reason with that knowledge. I think that's a more promising path towards true reasoning.
I like that. But how do you represent space and time symbolically? That's the tricky part. I mean, we can use coordinates, but then you run into the problem of translating between different coordinate systems. Think about how we can effortlessly switch between thinking about a location in terms of GPS coordinates, street addresses, or even just visual landmarks. How do you encode that kind of flexibility in a symbolic system?
That's a huge challenge. I think one approach is to look at how the brain represents space and time in terms of relationships. It's not just about absolute coordinates, but about relative positions and movements. We need algorithms that can natively understand and manipulate those relationships. Recent studies on the neural correlates of reasoning show intricate interplays between neural networks and symbolic reasoning.
But isn't that what transformers are doing? They're learning relationships between words in a sentence, which is essentially a representation of space and time, the order of words in a sequence. And they're doing it on a massive scale, with billions of parameters. Isn't that a form of symbolic reasoning, just implemented in a distributed neural network way?
I don't think so, Otto. Transformers are good at capturing statistical correlations, but they don't actually understand the meaning of those relationships. They can predict the next word in a sequence, but they don't know why that word is likely to occur in that context. They're missing the deeper semantic understanding that comes from symbolic reasoning.
And they're inherently limited by their sequential nature. They process information one step at a time, which is fundamentally different from how the brain works. The brain is constantly integrating information from multiple sources in parallel and updating its representation of the world in real time. That's why I think spatiotemporal awareness needs to be built in from the ground up.
Right. Current deep learning lacks the power and adaptability of biological systems. So it's about building AI architectures that can achieve that kind of parallel processing. I mean, if we understand how the brain's different areas interact during complex reasoning, it suggests a roadmap for designing AI architectures that can achieve parallel processing in language tasks.
Okay, let's say we agree that we need to incorporate more biologically inspired mechanisms into AI. What specific mechanisms are we talking about? Are we talking about spiking neural networks? Are we talking about neuromodulation? What are the concrete steps we can take to move beyond brute force deep learning?
I think neuromodulation is a really interesting area. It's about how the brain uses chemicals to regulate the activity of neurons and how that regulation affects learning and reasoning. We could potentially incorporate similar mechanisms into AI by using different types of nodes or connections that have different properties, and then learning how to modulate those properties to achieve different reasoning goals.
I'm still stuck on the spatiotemporal thing. I think we need to develop new data structures and algorithms that can natively represent and manipulate space and time. Maybe something based on graphs, where nodes represent locations or objects, and edges represent relationships between them. And then we need to develop algorithms that can reason about those relationships, taking into account the passage of time.
Exactly. The potential for incorporating neurobiological principles like neuromodulation into the architecture of language models to enhance their adaptive reasoning is exciting. This could lead to significant improvements in learning and problem solving. The study of the brain's plasticity in adapting to new information provides a crucial model for understanding how language models can achieve parallel reasoning.
So let's say we're successful in building these more biologically inspired AI systems. What are the potential applications? I mean, beyond just building better language models, what are the real-world problems that we could solve with adaptive parallel reasoning?
I think one area is robotics. Building robots that can navigate complex environments, interact with humans in a natural way, and solve unexpected problems. That requires a high degree of adaptive reasoning, and it's something that current robots struggle with.
Absolutely. Self-driving cars too. They need to be able to understand their surroundings, predict the behavior of other vehicles and pedestrians, and make split-second decisions in complex and dynamic situations. That's a perfect example of a problem that requires spatiotemporal reasoning and adaptive learning.
And think about medical diagnosis. Doctors need to be able to integrate information from multiple sources, patient history, symptoms, test results, and reason about the underlying causes of a disease. An AI system that could assist doctors in that process could potentially save lives.
Okay, but let's be realistic. We're still a long way from achieving that kind of level of intelligence. What are the biggest challenges we need to overcome?
I think one of the biggest challenges is data. We need to collect more data about how humans actually reason and then use that data to train our AI systems. But it's not just about collecting more data, it's about collecting the right data. We need data that captures the nuances of human reasoning, including the errors and biases that we're all prone to.
I agree. And we need to develop better tools for analyzing that data. Current machine learning techniques are good at finding patterns, but they're not so good at understanding why those patterns exist. We need to develop techniques that can extract the underlying reasoning principles from the data.
And we need to find better ways to evaluate the performance of our AI systems. Current benchmarks are often too simplistic and don't really capture the complexity of real-world reasoning. We need to develop benchmarks that are more challenging and that better reflect the kinds of problems that humans face.
So, where do we go from here? What are the most promising research directions in this field?
From my perspective, future research should focus on neuro-symbolic methods to bridge the gap between neural networks and symbolic reasoning. We need to explore more sophisticated mappings between abstract representations and neural processes, and ultimately develop AI systems that can reason, not just react. A focus on integrating data-driven learning with biologically inspired representations is crucial.
I think analyzing the specific parallel processing techniques used in current language models is key. Which aspects of parallel reasoning are most crucial for enabling adaptive intelligence? Can these algorithms be readily translated to other domains or models? Quantifying the rate of improvement in these models to see if we are truly approaching AGI is vital as well.
I'm advocating for more research into neuro-symbolic AI models. We need to explore how these models can incorporate both symbolic knowledge and the advantages of neural networks. If neural networks are not the only solution, what alternative approaches might offer a more robust and explainable pathway towards intelligence? The current focus on deep learning seems to neglect the crucial role of symbolic representations and logical reasoning.
I think we need a fundamental rethinking of how we represent space and time in AI systems. We need to develop algorithms that can natively understand and manipulate different spatiotemporal representations and that can seamlessly translate between different coordinate systems. If we can achieve that, I think we'll be a lot closer to AGI. More specifically, it would be great to see more research that directly incorporates spatial temporal reasoning during the network architecture design.
Those are all excellent points. It seems clear that learning adaptive parallel reasoning is a complex problem that requires a multifaceted approach. We need to combine insights from neuroscience, computer science, and mathematics to develop AI systems that are truly intelligent and adaptable. Thank you all for joining me today on Cognitive Spirals.